Okay, so continuing with the sessions, the next session is about Falcon, which will be presented by Google and Intel. It's their innovative work on things that they've been doing to improve latency, throughput, quality of life, air, etc. for everybody. Hunger? Sorry, world hunger as well. So we'll start in. Oh, yeah, hunger has been addressed as a side effect. It wasn't the primary design point. So take it away, Nandita.
Thank you, Sajid. I don't know if I can live up to that. Yeah. So, good afternoon, everyone. I'm Nandita, and I'm here this afternoon to present Falcon, which is a reliable, low latency hardware transport for NICs. And I'm here to present along with my colleagues at Google and our collaborators at Intel. So this talk, as I said, is going to consist of roughly 3 parts. In the first part, we'll look at why did we actually even go about thinking of Falcon? Why Falcon? Why a hardware transport? Right? Some of the motivation and thinking behind it. We'll then give you an overview on some of the key insights that have gone into the design of Falcon. A quick view into the performance numbers, very small scale. And then my colleagues are going to talk about the software components involved in Falcon, along with the relationship to the community at that. So rethinking transport in NICs. Why, right? Why did we actually set out? There were 3 main drivers on why we set out. The first and foremost are the new and demanding demands of the newer workloads, right? Including many of which are being talked about here and elsewhere. I mean, people in this room and elsewhere are living and breathing AI, ML. AI, ML, HPC, high performance computing workloads bring in new demands of high burst bandwidth, high off rates, and predictable low latencies. Not just that, we wanted to serve these new workloads, but also continue serving the existing workloads, right, of analytics, RPC, storage workloads. And what we found over the years is there have been incredible optimizations into many of the software, including those that talked about here, some that we deploy internally, such as Snap. Over the years, there are many optimizations that have gone in. There came in a point where we hit a wall, those optimizations. We needed order of magnitude improvements with respect to supporting the demanding needs of these workloads much more efficiently with lower CPU costs. That was one of the key drivers to actually consider moving the transport to hub. And ultimately, finally, the third reason is that our deployment experiences gave us a glimpse of what's possible to support these workloads for low latency on existing Ethernet, data center Ethernet network without needing specialized or niche networks that are, there. So these were the 3 main goals, and we found ourselves asking, hello, can you hear me? Yeah. Thank goodness for that, not lack of echo that's there. Yeah. So we found ourselves asking, what would it take to achieve low latency, high bandwidth, so basically high performance, isolation, and efficiency of these workloads on today's data center Ethernet network? Right? Our answer to that was Falcon. Falcon is a reliable, low latency hardware transport that exists over today's data center Ethernet network. And it didn't come out of vacuum, right? It actually integrating over our experiences over a decade of essentially iterations and production deployment experiences with these workloads iterating towards lower tail latency, higher bandwidth, and better isolation and more efficiency. We've just sold essentially a small set of specializations that we've observed to work well in production over these years into Falcon. Some of these, like delay-based congestion control, like Swift, um, with precise and timely retransmissions, right? Many of which actually are also available in some of the software, along with all bundled under multi-path connection. So over the next few slides, I'll give you a brief overview of Falcon and with a deep dive into some of the aspects. As I said before, Falcon is a multi-protocol reliable transport. It is built in support of industry standard protocol, including RDMA-based ID words, NVMe, and there are options for custom upper layer protocols. Three key pillars of Falcon, they are three things. Our first and foremost concern, our first and foremost requirement was tail latency, a tight tail latency for workloads, right? And there were essentially three tenets that allowed us to achieve this tight tail latency. Per packet based hardware assisted timestamps on a size fine-grained per packet basis allowed us to construct an excellent delay-based congestion control, works on an end-to-end basis. Selective acknowledgement or timely, precise packet delivery from recovery from packet losses. All bundled under multi-path capable connections because data centers are known to have multiple paths between any source and destination nodes. And we want to be able to use as much of the bandwidth possible for every single operation. And we bundled all these under a programmable engine that allows us to evolve and make changes as needed to some of these congestion control and multipathing capabilities. The second pillar is isolation and visibility at scale. When operating this transport or various kinds of workloads, some of them are byte intensive, some of them are latency sensitive, some of them are IO intensive. We need to be able to achieve isolation across these workloads, sometimes over a shared infrastructure. We put in capabilities for isolation, and I cannot overemphasize the importance of telemetry and monitoring. It's quintessentially helpful to be able to operate a network. And finally, for efficiency purposes, these capabilities are bundled in hardware over, as I said, supporting industry standard interfaces with optional, PFC encryption, etc. This gives you a very high overview mental model of Falcon. At the topmost is the upper layer protocol, which essentially performs the main responsibilities are interfacing with Falcon, providing flow control, etc. Besides that, Falcon itself is divided into a transaction layer, which interfaces with the upper layer protocol using a request response transaction interface. Its main responsibilities, as we will see, include ordering, fueling, resource management on the NIC. And the lowermost layer is the packet layer that interfaces with network and performs more traditional functions of the network, including reliability, congestion control, traffic shaping, pacing, multipathing, load balancing, and so on. So, in the next few slides, we'll just look at each of these layers very briefly, and then we'll look at numbers. Mapping upper layer protocols to Falcon. Falcon supports the industry standard interfaces, the RDMA ID words interface, right? This was important to us. It was important that we support lift and shift applications that are able to directly function when moved from on-prem to Google Cloud. So we support reliable connect and unreliable datagram, two-pair types, and these are strictly ordered mode where there's in-order placement and in-order completion. There's some amount of on-NIC buffering depending on the implementation of Falcon, whether it's constrained resource or unconstrained resource. Some amount of buffering is needed in order to support out-of-order delivery from the network, such as what happens under packet losses or under reordering. We also have an enhanced interface, which essentially introduces a couple of relaxed ordering modes where weekly audit, where the completions are in order, but the data can be placed out of order in memory. And then also a new type of error mode that we call complete in error and continue, CIE, where when errors occur, it signals an error to the application without tearing down the queue pair or the connect. The transaction layer is essentially sandwiched between the upper layer protocol and the packet delivery layer. It offers, as I said before, a request response transaction to the ULP, and wherein a transaction is a request received from an upper layer protocol and a response delivered to the upper layer protocol. So essentially, the IB words, reads, write, atomic, and are mapped as in request response. The transaction layer does optional ordering. It essentially follows the ordering semantics commanded by the ULP. Every connection can be configured to be ordered or unordered. It also does scheduling transactions, scheduling of all sorts, including connections, transactions, as well as imposing quality of service policies, and manages any finite Falcon resources depending on the implementation. Packet delivery layer is sandwiched between the transaction layer and the network. And as I said, it performs the more canonical functions of a transport, which include the end-to-end reliable delivery, congestion control, multipath, load balancing, are the three primary functions of the packet delivery. What I'm going to go through in the next 4 slides is just a little bit of a deep dive into the delivery layer. There is more to talk about the transaction layer, etc., but that'll be for a different talk. We use the Swift congestion control as a baseline congestion control for Falcon. Those of you who may not be aware of Swift, Swift is a delay-based congestion control that we've deployed in various flavors in our software. It is essentially a delay-based CC that achieves low latency, high utilization, near zero packet loss, implemented completely at end host in the case of software, or on the NIC in the case of hardware transport. And it can support a diverse workloads, like some of them which are throughput intensive, some of them are just IOP intensive and don't exercise the fabric that much, but exercise the host stack and the NIC quite a lot, and some of them are latency sensitive. The key aspect in Swift is essentially it precise RTT measurement that it gains through measuring these 4 timestamps that I've listed out here, T1, T2, T3, and T4. What is shown out here is life of a Falcon packet in the forward direction and its acknowledgement in the reverse direction. T1 and T2 are essentially the TX and the RX timestamp in the of data packet in the forward direction, and T3 and T4 are the TX and the RX timestamp of the returning ACK. Using a combination of hardware and software timestamps, you're able to essentially disambiguate where exactly the congestion is. It's important to be able to know congestion that happens in the fabric versus that which happens, say, in the remote host, in the remote NIC, So these timestamps allow us to disambiguate fabric congestion versus the host/NIC congestion and respond to each of these separately. And one can imagine that with synchronized talk, which is happening in data centers, right, we can even get one-way delay. So this is largely the baseline that is offered in Falcon. And we'll look at a few aspects regarding programmable congestion control going forward. Congestion-aware multipath network load balancing, very important for data centers. Data centers, as I said before, typically fat tree topologies offer multiple paths between any source and destination pair. Our overarching philosophy in Falcon is that every operation should be able to use the entirety of the bandwidth that is available between a source and destination host and be transparent to the applications. So Falcon provides native support for multipathing, wherein every op is able to use the bandwidth in a congestion-aware manner. And what I mean by congestion-aware manner is some of these flows are going to be, some of these paths between source-destination pairs are going to be high bandwidth. Some of them are going to experience congestion. The paths which are high bandwidth are going to pull the packets from the data op, right, more naturally, whereas smaller number of packets will just naturally go through the higher congested path. Over time, the paths that are congested are going to be repathed to more congestion-free. All of these are done transparent to the application. And it's also done in a way that you don't confuse reordering with packets and so on. But naturally, when you're spreading your op across multiple paths, not literally spreading, but in a congestion-aware manner, there are chances for reordering that can occur. I won't go much into this, but very briefly, as we were deploying with multipathing and protective load balancing in the network, we just found ourselves over and over again asking, like, what is the minimum available bandwidth along the path? Right? Because so far we've been operating on end-to-end signals. What is the maximum per hop latency along the path? Or what is the minimum utilization or the maximum utilization along? We wanted to know the characteristics of these bottleneck hops along the path of the packet. So that's kind of when congestion signaling came about. I'm not going to go into the exact specifics. It doesn't really matter where exactly it is in the header. There are many other places. There are many ways of actually placing congestion signaling in the within the packet header. What really matters is that this information carry the data from the bottleneck hop along the path, and it's reflected in the transport headers. Ultimately, it's the sender that's modulating rate, that's deciding how many paths to use for this particular op, how to load balance these paths, and I want to be able to use this information at the sender. So this information is essentially reflected from the receiver to the sender in Falcon header. The final bit that I'm going to talk about with respect to the packet delivery is timely and precise loss recovery, which is done via selective route. In fact, this community has actually done pretty extensive and impressive work on timely and precise loss recovery, and we've largely adopted what has been very successful in software, right? Which essentially is a sliding window for reliability along with the use of selective acknowledgement, wherein the receiver informs the sender precisely the packets that are received versus the packets that are missing. The sender uses this information, say, right? Both in congestion control, but also to be able to retransmit the lost packet in a timely. This is in sharp contrast to some of the existing incumbent hardware transports, which actually sometimes do a really bad job of retransmitting, right? And succumb to go back and recovery style. And many of the advancements here in Netdev, including the recent acknowledgement, the tail loss probe, I think are all very applicable in this scenario. Finally, programmability via rate update engine. We've bundled all of this in a programmable engine. What I mean by that is if you tease apart multipathing, load balancing, congestion control, it essentially comes down to three parts. First is eliciting a signal from the network, whether it's RTT or ECN or congestion signaling, right? And that's done in the hardware. The second is using the signal in some fashion, right, to be able to repath or to decide the number of multipath flows, decide which path should be given more weight for transferring and off, or to be able to modulate the congestion window. So all of this functionality is the second point, is essentially bundled in the rate update engine, right? And we made it programmable. And the third part is essentially enforcing the rate or the congestion window or enforcing the particular path or an op to take. And that's, once again, that's done in the hardware, in the Falcon hardware. So we've given plenty of thought to the rate update engine to be able to have a clean interface between the hardware and the software. Rate update engine, it runs on one of the ARM cores. On the next, we just need one core right now to be able to drive congestion control for 200 gigabits per second. And one might, and we've given a lot of thought, which essentially there are events that come in from the hardware. These events consist of hardware timestamps, the remote buffer occupancy, the number of packets asked, and so on and so forth, right, along with some other information. And the responses are the interpacket gap, the fabric congestion window, the congestion window for essentially to enforce the NIC congestion window in case the remote NIC of the host is congested, and so on and so forth. Now, we've designed this rate update engine a few years back now, and ever since then, we've had a few learnings from production. I think it has actually stood the test of time where we were able to translate some of the learnings from production and evolve the algorithms in the rate update engine, right? So that was kind of nice to know. We didn't, without having to change the interface. In the next three slides, I'm just going to give you a very quick preview of its performance on a small scale setting. Numbers with larger scale is something that we plan to share at future in future days. This particular plot just shows essentially write latency for a single queue pair. Our focus in mind is on predictability. I care about really how close is median, the average, and the tail, right? And if we compute the ideal that actually can be achieved through this, how close are we to the ideal? This graph essentially shows that as we vary the message size, larger messages, the P99 latency, the median, and the ideal match across the different message size. And so does it as you increase the number of connections. As you increase the number of connections, in this case, it's an incast, so there is more queuing built up, etc. And Swift is clamping down the congestion window as you build up, which is on the right-hand side, you see the blue line, which is the fabric congestion window goes down as the number of connections increase because it's a shared bottleneck. NIC congestion window stays high because the congestion here is in the fabric and not the NIC or the host. And once again, the P99, the P50, the average latency all line up with the computed ideal. Where it does not, we would always want to know what in the bottleneck is causing the added. Scalability under packet losses. This is important one as well, because it starts to matter when you deploy these transports. On the x-axis is the drop percentage, where this is a single QP again. On the Y1 axis is the bit put, and Y2 axis is the latency. And as you can see, as the drop percentage increases, the takeaway is really that there is a graceful degradation in the bit put. Protocols which cannot function well under increasing packet losses, you will essentially see a deep dive down in the bit put as packet loss increases. That latency also very gracefully increases, and there isn't an over or an alarming amount of retransmission. To end this part of the talk, Falcon is, in summary, a low latency, reliable transport that we built for essentially to be able to scale the demanding needs of these workloads over data center network. It matters. It matters for these three reasons, right? At the end of the day, it gives us predictable latency for the workloads. So I want to be able to, be able to confidently say that when an application complains or customers complain, the network is not, or my application is slow. I don't want it to be the network, be anything else in the stack. I don't want it to be the network. So predictability is really important. And, but to be able to achieve this predictable behavior, efficiency at scale is also key. And that's what it delivers by putting these capabilities in hardware. It allows us to scale the messages, the operate, and the number of connections or queue pairs. And at the end of the day, well, it does meet the critical requirements of the workloads that we see in cloud, HPC, AI, ML, but don't forget the old workload too, which is storage and PC. With that, I've passed on to my colleague, Nilesh, who will talk about the software components.
Thanks, Sangeeta. So in this section, we are going to dive a bit into the software components that enable applications to use RDMA Falcon and the components that enable the operators to operate the network. In this diagram here, you can see the RDMA Falcon is fully offloaded into hardware, and that's represented by this blue horizontal box here. This yellow box here represents the compute node, any commodity hardware running the application stack, either in host or in a VM. And the blue box here represents the IPU's compute complex is running on the NIC. The key takeaway here is that on the compute node, none of the software components are Falcon aware. The application deployment environments are all using standard off-the-shelf commodity software, along with Intel's upstream software, which is really modified for the Intel NIC, not really Falcon aware. All the Falcon awareness is actually taken off onto the IPU compute complex, where we have different applications in the user space accessing the driver to manage the NIC. And so subsequent sections, we'll talk a bit more about these components running on the IPU complex, which are really Falcon aware. Starting with the application interface, like means reinforcing again and again, like Falcon supports standard IP verbs interface. The applications work without modification. We support user space verbs under libIP verbs using reliable connected QPs and UD or unreliable datagram QP pairs. We support kernel verbs typically used for RDMA connection management or RDMA CM. The control plane used to set up Falcon connections are fully offloaded from the compute node onto the IPU cores. And the hardware data path is fully offloaded under SR IOV. We do offer some optional software and hardware features of RDMA Falcon. For example, Intel supports the optimized lib fabric provider called PSM3. We have a notion called virtual traffic class, which allows operators and applications to select and deploy multiple performance profiles for the system in production. We natively support 8K MTU. We have special kind applications can choose to leverage completions that indicate whether a UD datagram is dropped. This takes away the need for applications to do out-of-band communications to identify about drop datagrams. And we also support some novel modes like unordered queue pairs, which support out-of-order completions and out-of-order data placement, which we find is efficient for very large operations. Diving a bit on the control plane aspects here, one of our main applications running on the IPU core is the Falcon control plane connection management app. This is a user space app that provides us with primarily 3 functions. It manages resource policies for SRIOV PCI functions. For example, an operator may choose to limit how much hardware resources can be consumed by a particular VM or an application. We support connection management for Falcon, and this is done in a bump in the wire model. This allows operators to apply and implement optional business logic for connection management. An example could be translating virtual IPs to physical production IPs. This is all done transparent to the host RDMA drivers application, which is how we support lift and shift. And the third, most importantly, is it supports the ability to manage the data path performance. As you heard, Nandita, like telemetry is extremely key for managing these NICs at scale in production. And so the Falcon control plane connection management app surfaces a bunch of telemetry used for monitoring, troubleshooting, and is associated with the corresponding configuration management to help manage those bottlenecks. Overall, like if I had to distill it, our key implementation philosophy is to use the IPU cores to enable cloud service providers to operate the NIC and support standard semantics on the compute node so that we can support lift and shift applications on the host and VMs. With this, I'm going to hand off to Chen to talk about connection management.
Thank you, Nilesh. Chen. I work in the Falcon's connection management. Challenge with the designing the connection management for Falcon is when it comes to RDMA, connection management has always been sort of an afterthought. Pretty much the standard connection management in the industry is called RDMA CM. Implements an kernel agent that it handles the connection setup, requests and responses using UD messages. But also there are a lot of RDMA software in the industry that uses out-of-band communication or other configuration-based connection setup schemes. So the way that we design the connection management is we separate the Falcon connection setup from the RDMA applications. The RDMA from the RDMA applications view from the guest VMs or the host, the connection setup is no different from any RDMA from any other RDMA applications that are running upstream. It always involves the three-step dance. The first step is always to for the RDMA to allocate the endpoints. For example, the protection domains, the memory regions, the completion queues, the QPs, all the resource allocation. The second step, regardless which connection setup schemes that the RDMA application choose to use, it always involves some sort of handshake with the peer. Given if it's RDMA CM, it's going to send the messages to UD traffic to UD channels. If out of band, maybe these messages will be sent to a UDP package or through a relay server. The third step, after the handshake, it always involves the final QP setup where the application supplies the peer information, for example, peer QP numbers, parameters, and the peer IP address to the queue pair through the modified QP commands. So from the guest perspective, there's no changes to any guest software or any software that writes for the RDMA Rocky will continue to function unchanged. And the way that we design these the connection setup scheme is allows scalable control ops by allowing parallel connection setup background. From the Falcon side point of view, we initiate the connection setup in the background by intercepting certain control commands. For example, the IB verbs create, modify, destroy queue pair commands, and same set of commands for address handles. Regardless which connection setup was used by the RDMA application, everything at some point will go down to these commands. And we intercept these commands and pass them to the software that runs on the offloaded IPU nodes, where we do this 5-step dance. After interception, we always do the resource allocation. We allocate the connection IDs. We initiate the congestion control and coarse parameters. We allocate these security tunnels. It works for both PSP, Paddywax security that Google uses. It also works for IPsec. And at a certain point, the connection manager that runs on IPU initiates handshake with the remote connection manager that actually exchanges these security parameters and connection parameters. And at the end of the day, the connection manager will interface with the Falcon hardware to actually bring up the connection and update the RDMA's queue pair and address handle, so that the RDMA entities will know which connection that it will interfere with. Now, putting these two views together, we have this comprehensive connection setup flow. I'm not going to have time to dive into the details of this flow. These words will be in the paper, and it will have all the there. Just a few points I want to highlight that for RC traffic, we always allocate one connection per queue pair, so the connection lifecycle is tied to the queue pair's lifecycle. The handshakes are initiated by the Falcon's connection manager whenever it's possible, whenever it feels it has sufficient amount of information to initiate the handshake. It's done opportunistically. Not all connection setup requests will pass, which is fine. At the end of the day, there will be a certain point where both parties will have the queue pairs and will have all the information available, and the connection setup request will go through and the connection will be set up. And also here we have the opportunity to integrate with the VPC and also integrate it with other business logic here, so that we can apply the other data path configurations. We can apply the VPC policies here. We can decide, do we want to let the connections go through, or do we want to decline? We also allow the parallel handshakes. So the performance, the connections per second performance that we see with the Falcon is comparable to what we see with the. In order to support the Falcon connection manager, we have certain kernel components that we enable on the IPU node. First of all, we have the Falcon CSR driver. This is the driver that enables the user space software to directly talk to the Falcon device. It exposes the register interface so that the software can directly bring up and tear down the connections. It can apply. It has interfaces for the software to set up the mailboxes so that it can talk to the Falcon hardware to fulfill the rate update engine needs. Another soft piece of internal components called the RCA, and for RDMA configuration assistant. This is a component where it allows the interception of critical RDMA commands, for example, the create and modify QP commands, address handle commands, to be intercepted and forwarded to the RDMA, to the Falcon's connection manager, so that we can hinge the connection setup on top of the QP setup. I'll hand it over to Nilesh.
Thanks, Chen. So the rate update engine is really the software component running on the IPU cores that implements programmable congestion control for Falcon. It implements Swift for Fabric and NIC post congestion. It implements congestion-aware multipathing and load balancing. Also provides APIs for per connection level congestion stack. Keeping an eye on programmability, Roo is implemented as a C++ engine running on the IPU core. When you have a programmable engine, you have to deploy it at scale. And keeping that in mind, Roo and Falcon are implemented such that we can roll out and upgrade Roo hitlessly. That is, when you deploy a new binary for Roo, the data path is not impacted in terms of performance or availability. Roo processes per connection data path event to per connection congestion control. It processes per connection data path events, generates corresponding congestion response, and does around 1 response per RTT for each connection. This means that Roo today processes around 18 million events per second on a single IPU core. And for this, we naturally use all sorts of programming tricks, like minimizing our DRAM interactions, batching events to reduce barriers, and so on. Roo can also be scaled up to more cores if required. Then coming to telemetry. Telemetry is essential for deploying and operating RDMA at scale. And so the way we thought of Falcon telemetry was to support 4 kinds of use cases. One is for operators to monitor the production fleet, for operators to debug the network performance and availability, so that when an application host VM complains that the network is slow, we can go and debug and figure out why. To surface telemetry to applications themselves for monitoring them, for debugging themselves, and then for tuning the end-to-end network performance. In general, we have telemetry for observing different bottlenecks within the data path. And our approach has been roughly to use latency histograms so that we have visibility into tail latency. We look at very granular telemetry for precise debugging. So this where possible, we have per connection statistics. Where possible, otherwise we end up with a per VM pair statistic for debugging virtualized applications in multi-tenant deployments. And we also ensure the telemetry collection has minimal impact on the NIC's performance. So putting this together, like telemetry is collected across the layers to work coherently to identify bottlenecks in the endpoint. So just to give a sampling of what that means, right? Like if you look at the operation going from the initiator on the left to the target on the right, at every block, we gather different kinds of telemetry, observing the bottlenecks at that layer. So for example, the initiator RDMA is looking at the op level histogram at the initiator NIC, the per VF and TX bytes. The Falcon layers are looking at the per VF latency for reliable transfer. So you can account for the reliability, and looking at fabric RTT, so you can identify fabric bottlenecks. Similarly, it's tracking per connection retransmit reasons, either coming in from Falcon or the rate update engine. Likewise, as you go on the right, Falcon and the responder is tracking out of order histograms for debugging out of order delivery from the network, and tracking how much latency is spent in landing that payload across the pipe to the target host. As the system of target and host condition. And this is roughly how this is just to demonstrate the whole process debugging at layers. With that, I'm going to hand it to Yadong from Intel.
All right, hello everyone. So I'm going to talk about I think the easy one. All right, so just a quick refresh of the key components we just talked about in last few minutes. So we have kernel drivers and user space library, right, running on the host and guest VMs. We also have a couple new kernel drivers for Falcon enabling and all the interesting control plane and connection setup, and the CC algorithm runs on the IP core as well. So we'll just talk about our plan for open source and upstreaming. So the first one for the host drivers and user space providers, Intel team will upstream this Intel RDMA driver, iRDMA driver, and the verbal provider patch very soon, pretty much in the next couple of months. So this is going to enable RDMA for this new Intel product line. We call this Intel IPU E2100 adapter series. So this is available to industry to basically try this technology, and that we're excited about this new product. And a little bit details about this IDM driver. So this is again vendor driver. It runs on an auxiliary device created by this IDPF driver. An IDPF driver is already in upstream. Many of you know this driver is intended to be standard driver. So it's already there in upstream. We also have a user space provider. We call this a PSM3 OFI provider. As mentioned earlier, this is optional. One good thing about this transport is it supports a standard ID verb, so you can use any of your ID verb-based provider or OFI provider, and it will work fine. But the Intel team will include additional performance optimizations for HPC AI machine learning workloads. This is to improve performance scaling. So this is a PSM3 OFI provider is already open source, and so any new patch for performance optimization will go to the GitHub project for the OFI providers. So that's a quick overview for the software components on the host and the guest VM. But more interestingly, for two kernel drives that we introduced to enable Falcon technology here. So basically, this is an RDMA configuration assistant driver. We call this RCA.ko. So this is a driver runs on top of another auxiliary device created by this new Intel driver. We call this IXD driver. This is the Intel switch driver, or maybe easier Intel control plane driver. So this IXD driver will be upstreamed wherever it's available. Intel team is actually actively working on this, and so we hope to get this driver out to community very soon. So once the IXD driver is upstreamed, we will upstream both RCA.ko and this is Falcon CS driver. For the user space components, we are going to open source them as well. So this includes basically pretty much two applications, right? One is for Falcon control plane connection management, and another one is the software update engine, which includes all the interesting congestion control algorithm Nadia was explaining. So by default, we plan to go to OCP, but we are open to any other recommendation, whichever easier way for community to get vote. We're just a recommendation, okay? So again, that's another quick overview for the software components in this IP computer complex. But just to be clear, this is a quite capable computer complex. Integrates several core CPU cores, so it runs a full Linux OS. So all the software components here with shown in these pictures are super critical. We want to upstream into kernel as soon as possible. So going forward, we will work with OCP and the community here to really keep involving this technology, bring all the latest innovations in reliable transport to an industry. Thanks to all the great work and innovations from Google team, Falcon as a technology brings 10 years of advance in low latency, isolation, and efficiency to hardware design. So we really appreciate that. And also, Google team has done all the great work and all the leadership to drive this into OCP. So the product specification are already published in the OCP. We have a link here to the GitHub project, which basically includes 3 protocol specifications. One is Falcon-based transport protocol specification, and then 2 apply a protocol mapping to this transport. Right? One is for RDMA over Falcon, and the other one is NVMe over Falcon. These are very well-written documents. For anyone interested in transport design, please download the documents and read all the details. We also have links for some of the previous presentation in OCP. There's a Google Cloud blog post as well to explain more details about this technology. For the new enhancement and all the new features enhancement in basically future generation, it will be released in basically the future version of this specification. So I think the GitHub project is the place for all the new release. So just keep that link and sorry about that. So another thing to note, Google team is going to open up this simulator for RDMA over Falcon. This is a very capable simulator. It will be very interesting for anyone try to introduce new features or just to validate the protocol. So this is another very interesting software components for anyone else to get access and to try it out. We're going to work with the community here as well to introduce some new capabilities. So Intel team and the Google team will work together on some of the patches to enable advanced capabilities from this technology. We have a few examples here. One we mentioned earlier. We need to expose 8KB MTU support. The current IBTA spec defines MTU up to 4K only. So we are in process to work with IBTA.org, basically change the IBverb specification for 8KB support, so it's easier to drive the patch into kernel community. We also talk about telemetry. We think it's necessary to expose some basic telemetry at RDMA layer, which will provide visibility at RDMA layer about the patient's latency, histograms, and other VF level performance metrics. And so that's one thing we are going to work on. And then, more importantly, we have this great capability. This is unordered connection and the completely in error. This is very interesting for all the new applications for AI, machine learning, HPC. We are going to work with that, enabling basically this requires changes in the purpose and the OFR provider APIs. The current solution we are going to take is use direct verbs. Direct verbs concept level basically are ioctals and are more flexible, so it avoids some of the dependency on the IBverb standard API changes. So this is our current basically use direct verbs to implement more like a control path API, like a new version of create QP, a new version of modify QP to expose this kind of unordered connection and other new capabilities. So any recommendation or alternative solution we can always consider. So but I think at this time that's our the solution. So this is pretty much the summary. I think I want to take this opportunity to thank both Google team and the Intel team. Falcon is a great technology. It takes a lot of people, a few years efforts to get to today. So we want to thank our team members, colleagues across both hardware and the software design teams. I think that's what we have. So we have time for Ace. So maybe you want to come here. So, anyone? Is there any another microphone? I think there's the one. There.
On a previous slide, there was the nice result of the P99 latency being very close to the median latency in a whole bunch of different cases. Note that there were several strategies that you guys employed, past learnings for achieving that result. I was wondering if you had any insight on of the various things that you did, and what was perhaps most impactful, ended up helping most to drive that tail down. Meaning, is it the sum of all of them together, but all of them did one outside driving that tail?
Right. A great question, Arjun. And what the particular setup that you've seen, since it's an incast and Swift is controlling the amount of queue built up and the throughput, I would say for that particular experiment, it was the Swift congestion control. However, you can imagine there are many other scenarios in the data center, so which we do plan to we will share subsequently. But in a different scenario, you could imagine a case where multipathing is actually going to drive that scale down, right? Separately, I think I don't want to just over focus on the sunny day scenarios. I think the failures and the rainy day scenarios are quintessentially important as well, right? In operational network. And when you bring down a link and there are link flaps and link fail, you could imagine a combination of multipathing and protective load balancing, right, is what is going to drive that scale down. So I don't know if that answers your question, but yeah.
So I had a follow up on that, right? So I think number one, do the mitigation. I think we sort of glossed over the mitigations, but there is, as you said, it's Swift-based sort of prediction of rate and then matching that. How well does it scale when you go to 800 gig? Number one. Number two, was this a simulation or project or measured data? Because if it's measured, how much do you have hardware effect starting to show up? Because at 800 gig, right, the numbers become very sensitive. You are going to have implicit scheduling effects trying to show up as in conjunction with network problems. How do you guys see that?
Great question. I think this one is measured data, so it is not a simulation. I think we are past the phase where we show you simulation data. We showed you simulation data a long time ago, and then we now kind of came to a smaller scale data, and I hope to definitely show you larger scale, right? So this is on real hardware. With respect to your question on 800 gig, like when we were working on, I don't know, way back, it was 100 gig. People used to ask, is it going to scale to 200 gig? And we found, it actually did scale. And now actually we find it scales to 400 gig. It scales. So I think, it is going to scale to 800 gig. Maybe it requires some changes, etc. But our experience from at least, 200 to sort of 400 was, yeah, I mean, the current set in the first order, it didn't require any major changes. But your question, I think, is also trying to hit at 800 gig. It's not just the network fabric queuing latencies, like other dueling related latencies will also become a major factor. And that's a valid. Yeah. So we did not test it on 800. So yeah. Yeah. Not that far. But I would not write it off. I think we'll have to deal with those. No. Yeah.
I have a question. So this might come off as naive, but can you explain the difference between a software protocol and a hardware protocol?
Yeah, that's fair. I think, Tom, my definition was just very simplistic, like software protocol, one implemented in software stack, right? Whereas a hardware transport is one that's implemented in the hardware.
So I guess my real question is,
than that.
the hardware part of the protocol, are you burning that in the ASIC, or is this some sort of programmable device?
Currently, it is in the ASIC, yeah. But going forward, I would love the whole thing to be programmable.
It looks pretty complex. So get it into a nice programmable hardware component and runs almost at the same speed. You get flexibility of programming.
No, I mean, I think we have to tease that out. It's not really fair to call the whole thing as complex, right? Like we actually teased out there are certain things that make sense to run in hardware, like the parts that we know how to enforce ingestion window, how to enforce a pacing rate, on which packets to retransmit, etc. The parts that we know work, pretty much know how they're intended to work. I think it makes sense to bake it into hardware. And the parts that we actually think require further iteration, right? There's a very clean interface between hardware and the rate update engine. So we made those programmable. Now keep in mind that this is the first generation, and this is right going forward. I do think that programmability is going to play a huge role in transport, and we should absolutely focus on that. But without being on facility, right? I think one of the actual deals of programmability has all been contributed while getting flexibility and efficiency. But I do think that we should continue on that. Yes.
Please. Also, can we make this the last question? Or is there one more that's really important?
You mentioned that you use delay-based congestion detection. For that, you need time synchronization across nodes in the cluster.
No, you don't require time synchronization. Without time synchronization, you're able to compute the round trip time. So, both the forward delay and the backward delay are
Okay.
right. With time synchronization, you're able to disambiguate the forward delay from the backward path delay.
Do you use any kind of common timekeeping protocol? Is it the NTP kind of thing used? Or is it something more?
You can use a variety of things, right? I mean, NTP, sure, but PTP, I guess, is more sort of more modern. And we have some other solutions coming up with more precise time synchronization that can be done in a distributed manner. Yeah.
Delay. Yeah, so if your CC algorithm, right, use a one-way delay, then the time sync between two nodes is necessary. But if you use a round trip, if you remember previous picture, T4 minus T1, both T1 T4 are from local system, so you don't need that time sync.
You actually use PTP, or what the protocol we're actually currently using?
Currently, we don't use it. We don't. It's not necessary. We just use the round trip delay. But in future, our plans are to basically use Swift along with clock synchronization, so that we can just use the one-way delay of T2 minus T1.
Got it. Okay, thanks.
Unless you really think you have to ask this question, there's a breakout session next. Who wants? You insist? All right, last one.
Nice talk, clean slides. So I have a question about the robustness of Swift, given that it's a delay-based congestion control. I was wondering, like, for scenarios which are scheduling delays, and you have like low priority traffic going on, how does it sort of maintains low latency and also achieves higher throughput? Because given that you're tightening up on latency, are you sort of losing on the throughput just to keep the latency in control?
That's actually a great question, and we've definitely rooted out a lot of the buggy experiences during our production, and this was a lot more problematic, I would say, with software stacks than it is with hardware. The precise per packet delay measurements done in the hardware are really crucially important for us to be able to measure the queuing delay in the fabric. So that is what gives us confidence that we have measured that Swift is responding to an actual queue buildup in the fabric. And if you're able to get the timestamps right, then we haven't really found a case where it is overreacting to a phantom delay and underutilized, right? And it is in the quest for these kind of questions where we definitely wanted more sort of explicit form of signaling through to kind of assist with or augment with proactive speed.
Thank you.